high as possible. Now, the first thing we need to do is make sure we've got a value of S. So I could stand here going, okay, it's about 53, so I could write down, well, alright, cent in metres, that would be 0.53 metres, but what we want to try and avoid is using phrases like it's about and try and do it much more accurately than that. So we will find our board rubber and try and do this properly. Set square. Place your set square against the ruler, line it up with the bottom of the ball, and now we can see that actually it's 52.8. 0.528 metres. Remembering that the 52.8 was me reading it in centimetres, but I'm actually reading it in metres, so I've got to divide it by 10. Sorry. Yeah. So now we've got the S, now we need to take some measurements of T. So the ball's already in place, the timer's reset, and we can click off and the ball will drop. Make sure we gather up the ball so it doesn't fall on the floor. .336. Now we'll just measure to the nearest millisecond. This has got 2 decimal points here, but we'll just measure to the nearest millisecond. I think a thousandth of a second is more than accurate enough for what we need. So we're then going to need to turn the magnet back on, reset, and go again. Replay the ball. Now, we've got a slight variation in the time, but it's so small that we're not going to worry about it. Reset, and we'll take one more. Made it quite easy for me because all 3 readings to that 3rd decimal place are exactly the same, which means that the average is just the same. Now, what we need to do is square that number. So if I just go to my computer and use the calculator on the computer, excuse me, 0.336 squared equals 0.113. Now, we've got a value for S and we've got a value for T squared, which would allow us to plot a point on our graph. We wouldn't normally do that until right at the end. So now what we need to do is reset the magnet, put the ball back on, and we need a new value of S, or a new value of our independent variable. Making sure we undo the right clamp. Let's just drop that down slightly. Now what we're looking for is 7 different values of S. So it doesn't really matter what values they are, but as long as we've got space for sort of 7 values, that's good. And then we just do exactly the same again. Reset the timer. Let the ball drop, and we get a new time, and I'm just going to assume that we just repeat the experiment, and let's imagine we get 0.319 and 0.320, and the average would be 0.319. And we could square that on our calculator. 0.102. And now we've got a second point, or at least we will have, when we've measured S. Excuse me, using a different ball. You need to use the same ball really. Diameter of the ball might be different slightly. And we've got a new value which is 0.470. Now, basically we're going to populate this whole table in exactly the same way, producing values of S and measuring T and calculating T squared. So we've got S against T squared, and we're going to produce some points which we can plot onto our graph. And it will look something like this. And of course, hopefully, it looks a bit like a straight line. It's not perfect, doesn't matter. Now, strictly speaking, you would expect that to go through the origin, so we'll just adjust that slightly. Now, at this point, what are we going to do? Well, use a bit of colour. If I measure, draw a triangle on my graph. Well, this value here, bring this back to my axis. Now, of course, you would be using a ruler to do this. And then we have a value here, a change in the value on the y-axis. And of course, that's actually a change in S. Delta, the symbol for change. And similarly on the x-axis, we've got a change here, which is delta x, and of course that's actually a change in t squared. Okay. Now, the gradient of the graph, which remember equals m, okay, and m is the change in the y-axis divided by the change in the x, and the change in the y-axis was S, excuse me, a change in S divided by change in the x-axis, which is change in t squared. Okay, so the gradient m is S over t squared. Now, if we go back to the equation at the start, just give myself a bit of space. Well, if we divide both sides, remember m we thought was the gradient anyway, which is a half g, but if I bring the t squared over to here, it becomes times on this side, it turns into a divide when it comes to this side. We've now got that S over t squared equals a half g. Move that slightly. And there's S over t squared is the gradient. So the gradient of our graph gives us a value for half g, which we just need to double, and we have a value for g. Now, the last thing I'd like to talk to you about is uncertainties in your readings. Now, halfway through, you may have noticed that I almost picked up the different ball bearing. Now, I don't know whether the diameter of the ball bearing is different, so I should use the same one, really, which is one source of error, perhaps, one source of uncertainty. Secondly, any measurements we're taking, S, I have to measure S. What is the uncertainty in measuring S? Well, this meter stick will measure to the nearest millimetre. Now, if I'm deciding is it 1 millimetre or 2 millimetres, then I could make an error of half a millimetre. If it was right in the middle, between, let's say, 1 and 2, I could be looking here, and I might round up to 2, or I might round down to 1, which means at this end of the ruler I've got an error of plus or minus 0.5 of a millimetre. Now what people often forget is that at the other end of the ruler it could be exactly the same error. So at the other end we've also got plus or minus 0.5 millimetres, and if we add those together, the overall uncertainty in the measurement of S is actually plus or minus 1.0 millimetres, which is actually the same as the smallest scale division on the metre stick. You can remember that every time. If you take measurements of voltage, the plus or minus uncertainty is the same as the smallest scale division on the metre. Okay, so we have to consider that. So there's an error or an uncertainty in S, which is plus or minus 1.0 millimetres. Now, the only other measurement we've taken is the time. And you might think, well, okay, this is measuring to milliseconds, but hundredths of a millisecond. Now that's a 10,000th of a second, and you might think, oh, that's supremely accurate, and we don't need to worry about it. However, if we just set this up to go again on this one reading, and I make a recording, there we go, then we have a reading of 318.59, and we'll just make a note of that now. Is it 0.59? Now, how accurate is that time measurement? Well, the problem is with electromagnets is that they hold on to their magnetism for a little bit, and it may be that the ball isn't actually falling as soon as I turn the switch off. There's a little bit of what we call residual magnetism, which is making it stick to the magnet for slightly longer than it should do. Now we can combat that by using just something as simple as a little piece of paper, turn the magnet back on, and put this on. Now, if we watch what happens, remember we haven't really changed anything else. All I've done is put the piece of paper in. Now this time, we have 315.25. 315.25. Now, the difference between those two is about, well, something